Well, hello everybody. This is Bill Johnson. I'm a professor in the Department of Geology and Geophysics, and I'm going to talk to you today about the tar sands of eastern Utah. This is work that was done by a whole bunch of different people, and it was done on a shoestring. It was not funded, except for, as you see at the bottom here, through advocacy groups such as Western Resource Advocates, Living Rivers, and the Great Old Broads of the Wilderness. So more about that later. But what I'm going to show you is basically a mix of scientific and political issues that played out here. And it was work that I did with graduate student Logan Frederick, who got her doctorate a couple of years ago, is now a consultant. And then at the time, undergraduates Mallory Millington and Jake Troust, both of who graduated with master's degree. Jake did one with me, and Mallory did one with Paul Brooks. And then professors Kip Solomon, Diego Fernandez, and Gabe Bowen all contributed to this. So this image is of a canyon on the Tabaputs Plateau in eastern Utah. And this area is noted as a potential fossil fuel resource. And so this talk's going to be about marshaling facts to correct what I saw as a regulatory underreach. You hear a lot of people complain about regulatory overreach, but in this case, I think they didn't do what they should have done to protect environmental, well, specifically to protect water quality. And so the regional energy opportunity that exists out there is well known. It consists of near surface tar layers as an energy resource. I should say tar sand layers as an energy resource. And so I'm going to talk about that. I'm going to talk about the costs, the conflict, the costs that is, to climate, landscape, and potentially to water resources, the conflict that arose because of the permitting of this site to allow disposal without liners to protect water, and the data absence that drove the conflict. And then finally, about getting across difficult ideas needed to allow people to recognize the value of the site. So that's the outline. What it looks like is this. The red line that you see on this Google Earth image is delineating the ridge that separates the Book and Roan Cliffs on the south side, facing Grand Junction and Moab, and then the Uinta Basin shown here, and the Uinta Mountains there. So that's where this is located, and Red Leaf Resources is one potential site for development, but there's a nearby one that this concerns being developed by U.S. oil sands at the time. And it's one of many potential development areas for oil, shale, and tar sand in Utah. And so these different colors show different things, but the designated tar sands areas are shown in red, and potential tar sands areas shown in blue. And you can see that this entire region is in blue. And so the geology of that region is such that you have these sedimentary layers that are tilted to the north, a little bit to the west too. And so the Book and Roan Cliffs are shown to the south of this blue line, and you can see the canyons that are incised into those upturned layers. And then the, oops, sorry, I'm trying to get this to go backwards. And then on the north side, you can see that the canyons also are incised on the north side, but they're not exposing as much stratigraphy because it's a gentler, they're going down the dip. And so they're not exposing as much stratigraphy. The stratigraphy we're interested in are the top few layers. The Parachute Creek member is this milestone and siltstone, and I'm not going to go into details on this, but the point is it contains this mahogany oil shale bed, and that is the target for the resource development, energy resource development. And below that is the Douglas Creek member, which is a sandstone mainly. And looking at the cross section, did that accidentally, but we'll move on. Looking at the cross section of this, doggone it, it keeps moving. The Book Cliffs are descending more steeply to the south, and the Uinta Basin slope is to the north, and you can see it's a very gentle dip in the rocks. And so, zooming in on those top layers, we've got the mahogany oil shale bed in this very thin line as M. There it is, M, in this very thin line up here. And it's right up near the surface. And above that, you have the upper part of the Parachute Creek. And it looks like actually both. The upper part and lower part are up there. And then the Douglas Creek is following below that. So below the mahogany oil. So that's the stratigraphy. What it looks like in an image is shown here. This is the top of the Tavaputs Plateau. It's, sage, rolling hills with sage, but this dark feature here right under the surface is that shale oil bed, okay, or tar sand bed. And it's got obviously very significant tar, which are compounds that are larger than those you'll find in, say, gasoline. And so they're less soluble, and they don't exist as a liquid at room or surface temperature. Instead, they're a semi-solid. They're a mixture of compounds, some of which would be liquid, certainly not crystalline solid, but they're not flowing liquid. And so there's just some example of some of the rocks. And if you were to look close, you'd see that there's trapped oil or petroleum in those rocks. So why they're still there is because petroleum hydrocarbons are not very soluble in water. And that comes about because, in fact, the hydrocarbons, which typified here by the simplest one of them, methane, CH4, the carbon and the hydrogen in that molecule have equal electronegativities, which means that the electrons are shared equally in those bonds. And in contrast, water, the electrons are not shared evenly. The electrons spend more time near the oxygen in those bonds because the oxygen is more electronegative than the hydrogen. And so water has well-known polarity, methane is nonpolar, and the rule of thumb is that like dissolves like. And so polar substances do not dissolve nonpolar substances. And you've dealt with this in terms of trying to wash grease without using soap and other nonpolar items with water. Oh, and there's a schematic showing the electrons spend more time near the oxygen. So basically, I said all this already, so I'm not going to say any more about it. Here's an example asphaltene organic molecule, very large, fused aromatic rings with some aliphatic chains, comprised mostly of carbon and hydrogen. And related compounds are polycyclic aromatic hydrocarbons, one shown here, benzanthracene. These are important compounds because they're not very soluble in water. They're in these tars. Here's an example of a pit that was dug at the top of the Tavaputs Plateau as an exploration for tar sands removal. And so you can see that, they're in the rock, they're in the sediment, and they aren't flowing, and they aren't going to actually dissolve in this form into water to any significant extent. But what U.S. Oil Sands wants to do is to dig that ore, crush it, and mix it, shown here, with hot water and a solvent. And the solvent, we'll talk about in just a bit, it is designed then to solubilize the compound. It is organic, and so it is compatible with these nonpolar organic molecules, and it will dissolve them. And so they then separate the bitumen is another word for those tar compounds, and they separate that from the sand and water mix. That's the goal here. And they do that through a dewatering process and then sell the hydrocarbons. So the plan was for them to then take this so-called clean sand after dewatering and dispose of it on site. And here's what the system looks like on the top of the Tavaputs Plateau, their processing center. And one thing to notice is the fact that that stuff is just under the surface of the Tavaputs Plateau. So if you're going to dig it up, you're going to cause quite a disruption to the entire surface of that plateau where you're going to dig it. And so that's one major concern. Another is, of course, climate concerns. You probably heard of the Alberta's tar sands and the disruption, environmental disruption that's been created up there. You certainly heard about the Keystone XL pipeline that would bring the petroleum hydrocarbons to the U.S. from there. You probably haven't heard about the fact that, these nonpolar compounds partition to our nonpolar cell membranes. We have nonpolar interiors of our cell membranes that are the hydrophobic tails of the lipid molecules that make up our membranes. Or I should say they're lipid tails, but they're phospholipids. So the phosphate group forms the polar outer layer of the membrane. So they partition to organisms. They partition according to a bioconcentration factor that increases dramatically with increased size of the molecule. So these numbers here, 100 up to 100,000, those represent the concentration in lipid layers that would occur in equilibrium with water. And so if the concentration of in the water is 1, say microgram per liter, the concentration in those nonpolar cell membranes would be 100,000 times higher. So bioconcentration is a major concern for these compounds, and they are well-known carcinogens. And in fact, they're the earliest recognized carcinogens, going back to the 18th century regarding chimney sweeps, but other workers that come into contact with these kinds of compounds for various reasons. And so the first toxicity studies were actually performed on these kinds of compounds. So what happened is that the Division of Oil, Gas, and Mining referred this to the Division of Water Quality to determine whether a permit could be provided for on-site disposal without liners and without monitoring. And so Western Resources advocates learned of this permit, which was granted, and drove a lawsuit against the Division of Oil, Gas, and Mining. The U.S. oil sands said that the solvent they were using, so-called D-limonene, would vaporize once you separate the sediment from the hydrocarbon mixture with the D-limonene. And therefore, you're actually remediating these sediments. You're removing the dangerous petroleum hydrocarbons from the Tavaputs Plateau and therefore making it cleaner. Our argument was, in fact, that the D-limonene bitumen mixture will not readily vaporize, which is true. The D-limonene by itself would, but once you've got it loaded with bitumen, it will not, and it will reside and as residual in those sediments. And more important, the bitumen compounds will be more mobile after mixing with the D-limonene. And we ended up having to go into a bunch of thermodynamic calculations, and in the end, the judge was understandably confused by all these this lingo and these arguments, and instead just decided, hey, there's no water at the site anyway to impact, and decided that the permit stood. The judge's decision was actually made on an absence of data. What happened is that, as I said before, U.S. oil sands mischaracterized the contaminant behavior, but it turns out that they also mischaracterized the availability of water at the site. And so I ended up getting dragged to the site to help provide data to look at this issue. And so I knew already, we'd argued about the fact that large organic molecules like benzanthracene or asphaltenes, they are not very soluble, about 1.6 micrograms per liter for benzanthracene. It's highly carcinogenic, so you wouldn't want to drink that water. But the point is they're relatively insoluble. On the other hand, once you've added delimonene to extract that compound and that mixture comes into water, well, that delimonene facilitates this dissolution of the organic compound. And this is the schematic of delimonene here, simple small organic compound. And now its solubility in water becomes 500 micrograms per liter, right? More than 250 times more soluble. That's a big change and a big concern. The absence of water resources at the site came from this publication by Holmes and Kimball in 1987, a USGS water supply paper, and shows this cross section, which basically shows on the south side the La Salles going on a transect across the Green River to the north. Okay, so basically showing this 5-degree dip of the Tavaputs Plateau sediments. They indicated using this very coarse image in this document that the mahogany zone up here where the tar sands reside are high and dry. There is no significant water in this system, that all the water is moving from in the Douglas Creek aquifer below, coming from the high mountains. Now they thought maybe the La Salles or possibly U.S. oil sands indicated, or the Uintas. So you can kind of in your mind flip this figure. But the point is they attributed the water, any water that was around there, to faraway mountains. And this is important because it's a reasonable argument when you have not been to the site, and when you basically when you haven't been to the site, because it's very different from what it comes across in that water supply paper. Also, what U.S. Oil Sands did was to put a large number of holes in the ground that they claimed never encountered groundwater. But what they were looking for, of course, was tar. So they weren't really looking for water, but they made this argument because they drilled 55 of them and never saw, as they said, significant amounts of water. So the judge bought that and made her ruling. And then a fellow named John Weisheit, shown here, who's in charge of living rivers, contacted me to go visit the site. And I happened to be traveling to Colorado anyway, so we stopped and spent some time with him. And I like to think of him as Willy Wonka, because he, was excited to take me into this place, and this place turned out to be a wonderland. It's beautiful. It looks nothing like the top of the plateau. It's lush. It's not only lush, there are meadows and there are copious springs in these meadows feeding a lake, for example. And so it turns out that there's ranching activities in these canyons, and the ranchers depend on the groundwater. It's their only source of drinking water and water used for any domestic purpose, but also for their livestock. The wildlife and recreationalists also depend on the groundwater in these valleys. So it was totally different from how it had been presented in testimony leading to the judge's decision, and it looks completely different from what you see on the surface of the plateau. So the question became, how could the argument have flown that there's no water to be impacted in these canyons? And one important aspect was the fact that the ranchers, there's two ranchers, Bert and Christine DeLambert, in this one valley here. There's other ranchers in other valleys, but in this one valley I'm going to talk about, they've been operating a ranch for almost 40 years, and they noticed that their springs were drying up just as U.S. Oil Sands was installing wells on the ridgetop in order to supply water to their process. And so we visited them. This is Bert and Christine in their ranch home, and nice people. And they were explaining to us, the things that they had seen. And their home is right here in what's called Main Canyon, right at the bottom of our picture. Not in the picture, but just below it. And the mining, processing, and disposal site is only a mile or so away up on this ridge. And they were installing wells all over this ridge to get their water. And so it's a real concern for them. And so what we decided to do was to check the chemistry of the springs and get a sense of whether or not we could prove or disprove that the water was coming from far away, or whether in fact it was coming from these ridge tops. Because when you're in the site, when you're down in the canyon and you see these springs, you get the sense that they're coming from above. But you can't do that, you can't prove it until you start to sample them. There's a picture from the other end of the canyon looking back at the lake and the Lambert Ranch, and we're basically right over the mining and processing site. So, Division of Water Quality, Division of Oil, Gas, and Mining said that the water in the canyons comes from either the Uintas or La Salle Mountains, quite far away. So, several tens of miles away. The state engineer said that the U.S. oil sands well that was 200 feet down into this ridge is deeper than the springs that occur in this canyon, and therefore too far away to affect the spring flow. U.S. Oil Sands also made the argument that this 5-degree dip in the sediments would take all water to the north. So any water falling on the ridge tops would not go down in this canyon, but would go to the north. And of course, they made the argument that 55 boreholes in the ridge that didn't show copious amounts of water indicate that there's no water in this ridge top. So this is the crux, or the point of the argument. And so these different advocacy groups funded us to do the sampling and analysis. And I should say also Global Change and Sustainability, I can almost say that word, funded some of the work done too. So that's Jake Troust and Valerie Millington. This is a bunch of teachers in training through the Master's Secondary School Science Training, plus my graduate student Anna Farnsworth, Dan Prady, some other folks, undergraduate Matt Morrison, and there's Eddie Pazmino, all working on this thing. And so, like I said, it's a beautiful place. There's Bert and Christine watching what we're doing. And we had to hold the activists at arm's length. They would be very interested in what we were doing, and they immediately claimed us as their best friends. But of course, we're trying to be scientists. We're not trying to be activists at this moment. And so we had to kind of keep an arm's length with them, although they knew where all the good camping spots were, so it was really good to know them. So here's what it looks like from the sky. This is the ridge between the Book and Roan Cliffs, which are to the south, and then the canyons, such as Main Canyon here on the north side. And so these are all showing sampling locations that we found for springs on both sides of the ridge. And so here's the story in terms of the chemistry. And this is a really messy plot, so forgive me. But what it shows is elevation on the y-axis and various parameters on the x-axis. And what we're doing is plotting the elevation of each spring and then, for instance, its temperature or its specific conductance or dissolved oxygen, pH, alkalinity is calcium carbonate, and then strontium isotope ratios. And what you see is there are definite trends. And if this water was coming from far away such that the differences in elevation in this canyon were negligible compared to the transport distances, well, you wouldn't be seeing trends. And so temperature's, a tricky trend to evaluate, other than though it tends to reflect the recharge elevation. And so what we see is that the higher elevation wells tend to show the somewhat lower temperatures. So there's a definite trend on both sides of the ridge. The specific conductance is a history, basically, of how much water-rock interaction has occurred. It's accumulated ionic component. And so you can see that there's a trend with elevation in Main Canyon as well as on the south side and the Book Cliffs. Dissolved oxygen is tricky because there's respiration and other processes that affect it. And so the trend here, lots of slop in the data. And so probably not worth focusing on that. pH, two different trends, one on the Book Cliffs and one in Main Canyon, both kind of messy. And as you know, probably also, pH is a parameter that is affected by multiple processes, including respiration as well as rock dissolution. It does indicate there are trends, and it's possible that the trends that are different in the two areas represent tapping different rocks, because of course you can actually have a different carbonate content in the Book Cliffs because you're tapping more layers there. But what's interesting is the alkalinity, showing very clear similar trends on both sides of the ridge, and most interesting, strontium isotope ratios, very strong on both spring sites in the Book Cliffs and in Main Canyon. And of course, again, you're tapping different strata, and so it's very possible, since strontium is associated with carbonates, that you'd have different relationships in the strontium isotopes. So these are the deuterium 18 oxygen results, and you can see that they roughly follow the meteoric water line. There is some for these particular values that show some evaporative concentration, and these happen to be the lower elevation springs. The strontium isotopes shown as 1 over the strontium concentration also show very, very strong trends. And most important are ages. And you can see that the sulfur hexafluoride recharge ages are all relatively young, in the 5 to 30 year range. Well, actually, in the 5 to less than 20 year range for everything except U.S. oil sands well 4, which is somewhat older, about twice as old at 30 years. And then I think the most compelling is the tritium age data, showing that all of these locations are some mix of modern and submodern waters, and well, and some are just outright modern. And the U.S. oil sands well is older, going back a few decades at least, right? So this indicates that this water hasn't been around that long, and therefore it can't have traveled very far. The springs represent water that was recharged locally, and therefore at the ridge tops, not at the Uintas or at the La Salles. So we wrote a paper on this, published it, and that ended up allowing an argument to be made to change the permit. So this 5-degree dip is what U.S. Oil Sands said would bring the water away from this deeper drop into Main Canyon and to the basin. And so we noted that that's true if these materials were perfectly impermeable outside of their bedding planes. But in fact, these rocks are fractured. It's fractured sandstones and siltstones. And so it is not going to be necessarily the bedding planes that controls the direction of flow. And in fact, it's very unlikely that they are. If you look at this photo, you can see this is extremely steep topography, and these rocks are all fractured. And so it's very likely that flow can work its way through the strata and not be controlled by the bedding planes. The other thing is that U.S. Oil Sands claim they hit no water, so we plotted the depths of their boreholes, shown here, and the elevations of the springs, shown here. And this is just to show you that this is the mean, there's a median, and 1% and 99% endpoints. And so you can see here that the springs, except for one, are all lower in elevation than the boreholes, which means they never got to groundwater. They were just looking at the unsaturated zone that the water transports through. So we had a hearing, and I was trying hard to get across the point that you wouldn't expect to see water in those 55 boreholes because the residence time of water as it transits from a rainfall or snowmelt event to the groundwater, that residence time is relatively short. And so you can't expect those 55 boreholes to have picked it up. And a person who's not a hydrologist would not really necessarily find that compelling. But then I think I came up with a reasonable analogy there. And what I said was, it's the same as looking out today, which was a beautiful blue sky day, and saying that it's impossible for water to come from the sky. Because in fact, it rains, it just doesn't rain all the time. And the time that it does rain, at least around here, is relatively short. And so I think I got my point across through that. And then US oil sands began to argue that they admit that the water is moving from the ridge tops downwards, but that it wasn't coming from the ridge they were developing from. The water in Main Canyon was coming from another ridge. And so I pointed out that that's probably magical thinking to think that it only comes from some other ridge, not the ridge that they happen to be working on. So in the end, we were able to get them to require monitoring. The fact is that the issue became moot anyway because the U.S. oil sands enterprise went bankrupt not too long after this. And right now, the oil and related prices are low enough that it's not economic to develop that place. But at some point, oil prices will recover. Obviously, they're going to be a smaller part of our energy economy in the future, hopefully soon, but they will hold value in some part of the economy. And so the pressure will be back to develop this area. So anyway, I hope that you found that interesting. And I guess I can't answer any questions, but if you have any, please feel free to contact me.